RCB reduces the time required to design and schedule columns by automating not just the design calculations, but the entire design process. The user is provided with enough transparency to give them confidence that they are achieving the most efficient design possible. Design and scheduling for large buildings is reduced from weeks to days, and for small and medium buildings from days to hours. The column design and schedule process in RCB has a few parts. Firstly, the model must be prepared so that the schedule can be run, so the columns must be labelled and a second order analysis performed. The next step is we let RCB produce a design based on some design parameters and a design strategy. We can then change these parameters to see if RCB can produce a more efficient design, or we can go straight to the next step and rationalize the design ourselves with user input values or column groups. The job that we'll be designing the columns for has approximately 10 typical upper floors, one transfer floor to a flat plate slab, and 2 typical basement floors. Before we can run the column design and schedule, we need to prepare the model. So the first thing that we need to check is, are the load combinations that we want to design for set correctly? So under input load factors, we expand this out. We see that all of the combinations we want to design for have envelope ticked next to them. And the other important thing is we need to have a fire load combination set as well. So for the fire checks to section 5, we need fire loading from a load combination. Now, other videos will show how to specify primary cases load combinations, but for the purposes of the column schedule, we need to have some ultimate cases set as envelope, and we need a fire combination as well. So we'll hit OK. The next thing that we'll double check is our material properties. So it's not so important at this stage, but we'll just have a look at it and see what's in there. So material properties are set. We just have some standard concrete grades input. We'll hit OK. We go to column types. So column type 1, 2, 3, 4 is linked to material type 1, 2, 3, 4. And rather than changing the type per column in the working area, we can quickly edit and check the materials by the material per level tool. So if we expand this out, we see all of our columns are currently set to type 2, which has the material grade 40 MPa concrete set. So why it's done like this is basically what I'm thinking about now is what is input in this table is my lower limit. The RCB software, the RCB Column Design and Schedule, can modify the concrete grade for us, but it's important that we don't start putting large values in here from the get-go. So for example, I'm leaving the basement as 40 MPa because we'd like to see what the design produces, and maybe the design can modify these concrete grades for us. So for example, if I was to put 65 MPa in the basement from the beginning, the program would use that as a lower limit, and then you know it may work as 50 MPa, we don't know. So we'll just leave it as a lower limit value for the time being, and we'll let the column design and schedule suggest some different values for us if they are needed. So in summary, the concrete grade that is modeled, so either in the material types per level or in the working area itself, this is the lower limit concrete grade that will be used by the column design and schedule. The next thing that must be done is that the columns must be labeled. So in RCB, all of our columns just have a unique index, so this is to help us identify them. However, this is not so useful when creating a schedule, so we need to assign a label to them as we would when creating a schedule on paper, for example. So this is done under Edit, Sort Labels, and we can do it by assigning the labels manually. So we assign a prefix, suffix if we want to, and then start clicking the columns like so to assign the labels. Or if I delete them, I can just let the program do it for me automatically. So I will sort by vertical alignment, hit OK, and I can see the numbers here on screen. So when we assign a label, what we've done is we automatically edit the label property of the column, and if we wanted to change this manually, we could either use the assign manually label tool, or we can just change it manually ourselves here. So we can switch off the column labels by going to Settings, Viewing Options, and going to Column Labels. So off if we don't want to see them, but they are still there. So we go back to Settings, Viewing Options, we just want them on. We'll keep it like so. Another tool that we can use, another feature that we can use, which we won't in this case, but just letting you know that it's available, is for every column, it has a property called Include Design. So by default, it is set to yes, meaning that any column that is modeled will be included in the design schedule and will be designed. Now, for example, let's imagine this wall was a was a pile wall. If we didn't want to basically include those column elements that are used to model that that pile wall in our column schedule, we would set that property to no, so it wouldn't appear. However, we want to design all of our columns in this case, so we will keep Include Design on. And before we can design the columns themselves, we need to perform a second order analysis. With the design complete, we can now go to Design and hit Columns 2009, so AS3600 2009, and we can have a look at our column design table. So what we see here, what the design table is, this is where the column design and schedule will be performed, where all the results will be displayed, and where we will perform our rationalization. So we see the column labels as we define them on the as the columns in this particular table. The rows are the levels, and we see the fire rating, the required FRP here as well. So basically, it looks exactly like a column schedule would as we would start to draft it up. The concrete grade that we input is also shown here, and the column sizes. So at the moment, all that we see is basically what the column design knows. So the concrete grade and the column size, and we also see the unique column identifier as well, the index. We couldn't previously modify the fire rating protection for the entire for columns, but we can do that now quickly. So for example, the basement levels need a high FRP, so I change that by selecting the cell, double clicking, and putting 120 minutes. So this will now, when the column produces its design, it will use 120 minutes for all of these columns. We can customize what is shown in these cells by hitting Customise Table, and for example, if we don't want to see the column number, we can switch that off. And we can also show things like the applied loads. So for example, the columns are pin, so we will switch off bending moment and shear force. So we can choose for what load case we want to display the results. So for example, if we were sending this out to a piling contractor, we could export whatever we see here on screen, we could send that out to Excel. So that's dead load, and we can also have a look at live load as well. Now we will go to step 1 of this process and let RCB produce a design for us. So RCB will modify all of the design parameters of the column except for the column size. The reason why we don't change the column size is that's the last thing that clients and architects want changed, so we don't do it automatically. However, you can change the column size manually if desired. Going to the Design Parameters tab, these are the global design parameters that will be used for the design. So we think of these as first pass values, which we can overwrite later if we want to. So the parameters are grouped by the parameters are grouped by the relevant section of the design, so strength, fire, shear and core confinement, and some general ones. And in this tab we can also select what aspect of the design is performed. So at a minimum the strength design must be performed, but for example if we wanted to see a bit more clarity in some of our results, we could switch off fire design, or we could switch off the shear and core confinement checks as well. So what we do here is we set upper and lower limits of the design parameters that the program will change. So for example, minimum and maximum bar sizes, minimum and maximum spacing, so the spacing in the section of the member. We specified a concrete grade of 40 MPa in the model, so the lower limit will be 40 and the maximum will be 65. So we set things like the maximum reinforcement ratio and the aspect ratio limit. What the aspect ratio limit is any column that has an aspect ratio of greater than 4:1 will be treated as a wall and excluded in the design. So if we were seeing some columns not being designed, it could be because of this limit. So we input our fire design parameters as well, our shear and core confinement design. So the tie size that we select, the program will first attempt to find a spacing that satisfies shear and core confinement requirements with a tie diameter of N12s. If it can't, it will then start increasing the tie size as needed. Concrete cover is basically the clear cover to the ties, and the effective length factors are also set as well. It's not done automatically. In recent updates, the B to D value is now calculated automatically per load combination, but we have the option of overriding it with a user-defined global value as well. In this case, we will keep it automatic and we can have a look at it in the reports later. Next, we set the design strategy. So what the design strategy is the order in which the design parameters will be modified by the RCB software. So again, the parameters are broken up by the relevant section of the design, and we can also choose to basically stop the program from modifying a certain parameter as well. So for example, if we don't want the concrete grade changed automatically by the software, we can uncheck this. So what we see here for strength design is that it will first change the number of bars before it changes the bar size, and then finally, if it can't find a solution, it will move up to the next concrete grade. Similarly for fire, we've done something similar. In this particular case, it might be more efficient to change the cover first before we increase the amount of steel, but we will just leave it as it is. We let the user change the parameters themselves so that they can find a design strategy that is most efficient. And the user has complete control over the design that is produced by RCB. With the design parameters and design strategy set, we can go back to the design table and start the design. So before we start running it, just a few things to mention. We can calculate and display the results either as a safety factor or as working percentage. So basically it's just the same thing. One is the inverse of the other. Safety factor simply is load divided by capacity, whereas working percentage is capacity divided by the load. So we'll just set that to working percentage. And we then set the type of reactions that we want to use. So the program calculates reactions via static analysis, so considering the stiffness of the frame when calculating the distribution of the loads, or area method, which is simply tributary area. We also have the option of static and area, and what this is, the program will design for the maximum of, or it will design for the worst case of static and area results. However, we can't run this from the get-go because we need to have run one design with static, one design with area, and then a third one with static and area to get the worst case design. For this example, we'll just stick with static. So we also have the option of designing individual columns, column groups, or individual levels, but we want to design everything, so we will just go ahead and hit design. Designing all columns for strength, fire, shear, and core confinement for all load combinations in the envelope. With the design complete, we now see a bit more information in our column design table. So the columns are now colored based on a color scale based on their safety factor or working percentage. And if we scroll through, so blue being working very comfortably to green, yellow and orange and red failing, and we also have this shear and fire failure. Looking at a few of these columns, the subscript S next to the column means that this was basically this design is governed by static analysis. So we've only done a static analysis, hence everything is S. We see the basically the bars, so 8x3 and 16s, and the steel as a percentage. The basically the way that the bars are displayed can be changed as well. So the default 8x3 and 16 can be changed to the total number of bars. So for example, going back to the same column, 18 and 16s. So depending on how the schedule is produced, how the number of bars are displayed, we can change it like so. Other things that we see the governing load combination for strength. We also see some safety factors as well. Covers the ties that were designed, all this other information. So during the design stage, it's probably very useful for us to see the governing load combination, things like the safety factors. However, when we produce the final design, obviously we don't show safety factors on there. So we can at any time switch off these values if we don't want to see them. Like so. Other things that we can see see from these results, we see that the working percentage for some columns is given in basically the XY, so circular columns biaxial direction. For these rectangular columns, we have X and Y separate, meaning that clause 10.6.3 was satisfied, and that this column has low eccentricity of the applied loads, hence we can consider the X and Y directions by themselves and not consider the biaxial direction. Going to this column, for example, we see the result is displayed in the biaxial XY, meaning we have a higher eccentricity and that the biaxial direction is designed for the worst case. Other things that are evident, we see that we have some additional symbols displayed occasionally. So in this case, the asterisk symbol means that this particular column had its design changed to satisfy fire. So we see this fire design governs, meaning that the steel was increased to satisfy fire requirements in this case. So maybe not the most efficient design from a steel point of view. If we go to the concrete grades, we set the program to change concrete grades automatically. The labels that are shown here in the concrete grade column, they're indicative of the basically the most common concrete grade that occurs within that particular floor. So the ground floor, a lot of the columns were changed to 50 MPa, and then we see a few others here that that have 65 MPa. So these columns, if F-C is not shown, we see that this 50 MPa governs, but for this column number 56, we have some additional value, meaning that 65 MPa is governing. Other things that we can look at in the design table, rather than seeing all of the columns, all of the column results, especially if the job is bigger, it might not be so clear. We can see just the columns that fail for strength. So it looks like only one is failing for strength. And we can also see the one that is failing in fire as well. In this case, it was unable to create a design just for the for the one column. We can also show the column, basically just a little image of the column cross section, which we can also use to when we start to rationalize the design. And other things that we can do, we can specify maximum minimum ranges as well based on the safety factor or the working percentage. So we only see columns that are that fall within a specific range. So this can also help us in the rationalization. We can see we can just isolate the ones that are of interest. RCB can also produce a series of reports. So if we go to this drop-down box, we have summary reports, detailed reports, material summaries, columns with maximum steel. So hitting this one, pressing report, the program shows us the columns that are basically working the hardest and all of the other columns. Now if we pull up the summary report for, let's say, column number 57, the one that's failing, we can have a more detailed look and see what's going on. So we expand this out. We can see the B to D factor is calculated by the program, the loading, the capacities, whether or not clause 10.6.3 is satisfied, and then the percentage in the X and Y and the biaxial direction, as well as the governing load case, in this case the 1.2G 1.5Q case. Going down to fire, we have a summary of all of the fire results. So for the column to pass, the top must pass and the bottom must pass. For the top to pass, we have to get a pass back from at least one of the tables. So here we see table 563 fails, 564 passes, 572 fails. Similarly for the bottom as well. So this symbol, this dash symbol, indicates to us that the column did not meet the criteria to use this table. Similarly for 5.7.2, meaning that the aspect ratio probably wasn't big enough to design as a wall. However, we could use table 5.6.4 and we did receive a pass. And then finally for core confinement and shear, the program automatically calculates the number of legs in the A and B directions, or the local X and Y directions, to satisfy detailing requirements to clause 10.7.3.1, and then some minimum spacing as well. So in this case, column was pin-pin, no extra shear loads, but it's all shown here in the summary. And then the final shear spacing is the maximum of the spacing needed for section 8. In this case, nothing, because there was no shear load, and the spacing needed for core confinement of 200 millimeters. So just a very quick way to get an overview of the results of an individual column, or we could spit this out for all columns. If we wanted more detailed reports, so if we wanted to find out why the column wasn't designing, for example, we could open up the detailed one column and basically see all of the iterations, all of the design results in great detail for a particular column. So it produces a lot of information, but can give us an indication of why it can't find a solution for that particular design strategy. Finally, we can also export individual columns to the RCC column software. So under export settings, we specify the fire combination and the ultimate combination. So in this case, we know load combination number 1 was governing, and we can set export and launch and export only. And how we would do that, how we export it, is after we have the settings set correctly, we right-click and export to RCC. With the design complete, we could attempt to modify the design parameters and the design strategy so that the basically the design results produced by RCB either work or are more efficient. So basically the materials produced are more efficient. However, rather than doing that, we're just going to jump straight into step number 2 and begin the rationalization process. So rationalizing the design produced by RCB. What we mean by rationalizing is that the design produced by the design table, by the RCB program, is a bare minimum needed to AS3600. Basically, it might not be the most efficient one based on the strategy that we've chosen, but based on what we've chosen, this is what is designed. So rationalize means we start grouping the columns, as we would in a normal design schedule, to something that is going to be easy to build on site. So we can do this in basically a few ways. We can do it using basically editing the design of individual columns, using groups, or letting the program do this automatically for us, attempting to let the program do this automatically for us. But first we'll have a look at the auto grouping. We'll have a look at this first because we're not actually going to use it in this example, but we'll just see what it is, how it works. So auto grouping works on, it attempts to find columns of similar loading within a certain proximity of each other and a certain basically floor range. So what it will do, if they have similar loading, we assume that they will have similar capacities, similar designs. So we will then create column groups automatically for them. Now, be careful when using this. If it's a larger job and if you have groups present already, this may produce some undesirable results. So ideally this should be used on a blank design without any column groups so that no information basically gets lost, because this may produce many column groups. We're not going to use it in this case. The first way we're going to try to rationalize the design is by using user-defined values. So we will try to get this failing column 57 working by modifying the design ourselves. So we go to Edit Column Design, and then we can start modifying the values. So the program basically, it hit the maximum concrete grade and pretty much the maximum reinforcement limit, close to the 4% that we've specified, and it's not close to working. So really the only thing that we can do, we're not left with much choice other than to start changing the size. So I'll hit dimensions and hit 300, then design one column rather than redesigning all of them, hit design. So now that is working, so just that extra 50 mil, we are now working with 40 MPa concrete. It's working relatively efficiently, so close to 100% of its capacity in the Y direction. So as bare minimum, it is working and we're happy. The next way we'll start rationalizing the design is using design groups. So how we define design groups is we can select multiple columns, either horizontally or vertically, right-clicking them and hitting Create New Group. We can also select other columns such that have the same dimensions and hit Add to Existing Group. So we'll put these in group number 1. And we will maybe make another group like so. Like so. So rather than designing all of the columns, we can design group number 1. So the program is performing 2 designs. It will design all of the columns individually. Then it will get the worst case results from those 4 columns, reapply those design parameters, and then redesign them again, so to get updated safety factors. We'll do it for group number 2 as well, and based on these safety factors we can then determine whether or not this particular column belongs in the individual group or if it doesn't. So now redesigning the columns again based on the worst case results. And we see the design results on screen. So when a column is in a group, we see the group subscript, which we can of course switch off when we export. Now the design values that we see on screen, this is just the bare minimum calculated by RCB. Similar to individual columns, we can edit the group design by selecting the values, and then we can modify them like so. If we basically, as the design progresses, if we don't want to lose any design results, so for example, if we let's say for argument's sake we're happy with the bar size N16 that was designed for this particular column and we don't want to lose it, we lock in this value by hitting the Edit tab, the Edit checkbox. So with this edit ticked, basically this value of N16 is locked in and will not be changed by the software. Let's say cover we're happy with as well, the tie size, the number of restraint bars is automatically done, but if we're happy with the bar configuration and the concrete grade, we can lock this in so that, for example, if the design is changed, if anything changes, these individual columns have all of these parameters kept, they won't be lost. So let's hit OK. We see user-defined values, we just have to redesign it again to get the design back. But basically, this subscript U means there's user-defined values that will not be lost if the design is lost. So what I mean by design is lost, if I hit this delete design button, which I'll do now just for demonstration, we've lost the design produced by RCB in all of the other columns, including this group where we didn't lock the values in. But for this group number 2, if we hit edit the group design, we see that all of the various values that we were happy with have been locked in and kept. So this will not change with that design, basically with those values locked in. If for whatever reason we wanted to scrap completely everything, get rid of our groups, get rid of the user-defined values, we would hit this delete user edited info button and then hit the design. So basically that's a hard delete that will wipe all of the user values, and then we can right click and delete all groups. Now for this particular column, this column number 57, we changed the value. So yes, it's basically the size of this column is different from what is in the model. Also, if we run the design again, and I'll just fast forward this. So with the design complete again, we did manually change the size of this particular column, but the program was also changing the concrete grades for us. Now let's imagine this job was in the preliminary stages. Any changes that we made in our design, we might not necessarily want to put them back in the model. So what happens is if this update building option is switched off, if we hit exit, basically everything is saved locally and nothing is changed in the model as well. So the concrete grades, the sizes will stay as they were when we modeled them initially. If the design progresses and we're happy with this final design, we want to put that back into the model, see what effect it has on our reactions, we would hit update building and hit exit. And of course we're given a warning that basically the column size and the concrete grade, these are the design variables, the design parameters that will be sent from the design schedule back into the 3D model. So in this case we'll hit no. So we continue the rationalization process here in the design table in RCB without having to print any information onto paper. So we can see everything clearly. We've got our detailed reports. We can send individual columns to RCC as well if we're interested in basically looking at particular things in more detail and viewing the MN interaction diagrams. Now let's imagine the design has progressed to the stage where we have finished it and we're happy with basically how it's all rationalized. So we now want to prepare what we see on screen for basically to send to a draftsman. So we just switch off the various things that we may not need for the column schedule. So for example, the group number, the column number, the working percentage, the exposure, the K factor. So we just reduce the schedule to the values that we're going to need just for the schedule. And then what we do is we, for example, hit export to Excel, and whatever we see on screen is sent out to Excel or DXF format. And there we go. And then this can be sent to the draftsman for drafting. In summary, what we've covered in this video is how we need to prepare the model in preparation for the column design and schedule in RCB. Then we've gone over what the RCB software does in the column schedule itself. So the two main steps, the RCB design, letting the program produce a bare minimum design to AS3600 based on some design parameters that we've set and a design strategy, and then how we can view the results and how we can rationalize the design. So the goal is mainly to do this all within the RCB software, so that we have to basically eliminate or reduce the amount of transfer of data from RCB to other programs. We also want to automate these repetitive calculations and basically have enough transparency, have enough confidence in RCB so that we know that it's doing what it should be doing.